Right. Okay. Um, has anybody gone through the 3061 or tried a few of those calculations we did last week? Okay, you have. And have there been any problems? Okay, Leila, that's great. Okay. No, that's fine, Andrew. Um, I just wanted to know if there were any problems or if you've got any questions. Do any of you have any questions for those sort of problems? No. Okay, right. So what I want to do today is do the complex ions and then move on to acids and bases. In this exam, you get normally 3 questions. One is pretty much based on 3061. One is based, 1.5 questions are pretty much based on 3062. And the other one is the 3063. It's sort of either a whole full question by itself or is only half a question. So, complex ions. Here's some more off by heart learning for you. And I'm a visual learner, so I like seeing pictures to help me remember. I hope this is clearer. First of all, is there a lot of noise in the background that's disturbing you or not? Some of you, no, it's not too bad. Okay, our copier has packed a hissy fit there. So, okay, so I remember things as ZAC and ZELP. If you did the CH 2.2 standard last year, you will have learnt complex ions off by heart already. Sorry, I've done the wrong thing here, so let me get rid of that green square, green arrow. Oh, it's not doing its thing. Ignore the green arrow. I don't know how I got it. You have to learn these off by heart. Now, I remember them as it says ZAC, and ZAC would stand for zinc, and the A for silver, and the C for copper. Okay, so if you look for the, I just want to try and get rid of this. Okay, if you think of the ammonia, okay, ammonia is a weak base, so I've made it in a lighter blue. Ammonia forms of 3 different ones. There's the copper, there's the zinc, and there is the silver. So that's one way I remember. And then the ZELP, because we've got 2 things starting with A, as you might have seen, silver and aluminium both start with A. So there's again another 3 for hydroxide, and that's again the zinc, but in this case it's aluminium. So the L in the ZELP is to make you remember aluminium, as well, of course, if you forget that the P stands for lead, at least hopefully the L will make you remember the lead. So I hope that's going to help you remember which complex ions you have to remember for ammonia and which ones for hydroxide. Who knows their complex ions? So either because you've done the booklet and you've learned things off by heart already, or because you did the standard last year and you've learned them last year. Okay, right, great. So that I hope that I've updated the teaching notes. If it's not in your teaching notes, you got your teaching notes before that was done. Okay, the other thing to try and remember is that all of the complexes have got 4 ligands. So the only exception is the silver ammonium complex, and you'll notice if I try and make this even bigger, that's the only one that's got 2 ligands there. So it's got 2 ammonia molecules around the silver ion, whereas can you see all of the others have got 4. So that is hopefully going to help you remember. So I'm trying to drag this over. Okay, that one's also, the lead has also got 4. So do you think you'll be able to remember them now? Okay, so find a way, if this doesn't work, find a way of memorizing them either by making an acronym or, as I say, I'll go by pictures. But it is important. It is nearly guaranteed. I've only found 1 year where they didn't ask about complex ions, and they were actually did sort of imply complex ions, and they were trying to trick you. That was 2012, I think. So make sure you at least know your complex ions, so you'll know when they're trying to when they're trying to trick you. Yes, they like being devious. So that's, as I say, basic sheer learning work. You've got to go and do it. It's like your organic functional groups. You have to just learn off by heart, and organic reactions you just have to learn off by heart. Okay, now that we've got those hopefully in our minds, remember ZAC and ZALP. So we've got zinc hydroxide complex and zinc ammonia complex. We've got the silver ammonia complex and the copper ammonia complex. That's ZAC, zinc, silver, copper. And then for the ZALP, it's the zinc aluminium copper. Zinc aluminium lead complex. So let's now look at this example. And whenever you see silver, in fact, I love a dichromate, a silver chromate. It sort of appears in nearly every second exam paper because it forms complex ions. So if I just change it to a green. If you ever see silver, think complex ion. Same thing for zinc, same thing for aluminium or copper. So what have you got here? You've mixed silver chromate, okay, and, well, you've got 2 of them, okay, but one of them is in just straight water and the other one is in ammonia solution. So I hope bells are ringing that complex ions are starting to come into your mind. And a good clue is when they say no calculations are necessary. If you see that, then it is likely that they're either talking that you've got to discuss things like Le Chatelier's principle, and it's most probably going to involve complex ions. So let me actually ask you, where do you think silver chromate is going to be more soluble in? Water or the one with the ammonia in it? The one with the ammonia. And the reason is, and it's the whole point of this lesson. Okay, some of you are typing. Okay, so it forms complex ions, yes, it's because it's in the complex ions. If they could ask you and have a beaker C where this had, say, potassium chromate present, okay, so if we had potassium chromate present, would my silver be more or less soluble in a solution containing potassium offline? Correct, and that's because of the common ion effect. So whenever they ask you questions, and especially if they say no calculations necessary, they are either talking about common ions, where something is less soluble, or they're going to be talking about complex ions, where it's more soluble. Okay, and there is a third one which you also come across in the teacher marked assignment, where it's pH as well, because an acid can react with a base, and we'll look at that briefly at the end. Okay, so what you need to do in this sort of reaction, this sort of question, is support all your statements with equilibria. You have to write down the equations, and when you discuss which way the equilibrium is going to shift from left to right, then state what equation you're talking about. Because if you just say the equilibrium position shifts to the left, if you haven't got an equation written, the teacher doesn't know which equation you're referring to or which equilibrium. So you would always start off by writing some sort of equation, and if you're not sure what to start, always start then with your solubility one, which is your solid. So you could write solid in here, and it forms your 2Ag plus the chromate. Okay, so you've got an equation there. What other equation could you write down? So quite a few of you typing. The formation of the complex ion, correct. So moving that up, you would then, the other one would be, is where you've got your Ag plus your, and because we've got it in ammonia, we react it with ammonia, and that will form. Now with complex ions, you must have square brackets, okay? You've come across square brackets now in a number of cases. When do we use square brackets in chemistry? For concentration, correct? So we use for concentration, for writing complex ions, and remember also, it's the same thing in terms of complex ions. Remember in your Lewis structures, you had to, if you had a cation or an anion, say you had to draw the Lewis structure for SO4 2 minus, remember you needed, thank you very much for that, remember you needed the square brackets, and then you put the charge outside the square brackets, just like the complex ions here. So that's the 3 cases so far you've come across square brackets. So now you might want to write here equation 1 and equation 2. It makes your answer much simpler by saying the equilibrium in equation 1 shifts to the left and to the right, you know, however you are explaining it, instead of trying to state the whole equation again. So to answer this sort of question, refer to the equation. So you would say in water there's an equilibrium established as an equation 1 with the ions of silver and chromate in equilibrium with the silver chromate. If however you put it into an ammonia solution, then the ammonia reacts with the silver. So this, and I'll just change my color. So the equilibrium position in equation 1 shifts to the right because silver ions are being removed. So remember Le Chatelier's, if a stress is applied to a system, and in this case the stress is removing the silver ions, the equilibrium position is going to shift to minimize that stress, so it's going to shift to replace the silver ions. So I'm going to get more and more of the silver chromate dissolving to try and replace those silver ions. And that's pretty much how you would explain this one. Any questions? Okay, none? Okay, right. If, now this wasn't in the paper, but say looking at my extra one, say beaker C that I had here, and you had to explain this one, then what you would have to say, you would just then have equation 1, and you would simply say, because there are more chromate ions in solution, by Le Chatelier's principle, the stress has been applied by supplying more chromate solutions, so this equilibrium position, notice I say equilibrium position, that's actually a much more clearer than to say the equilibrium changes. It's really the position, the relationship between the concentration of products and reactants sort of change. So the position changes so that I get the dichromate tried to be used up so that the position, equilibrium position shifts to the left. So that's a case of a common ion. Okay. The relationship, by the way, just in case that didn't make sense, the relationship between products and reactants is always fixed at a particular temperature because it's a constant. So you'll always have that. But if you add something, you do have to try and remove those dichromate to try and so the equilibrium position shifts to try and keep the products in the same ratio to the reactants to fit the Ks. Did that make sense? Because I think I actually said something slightly wrong earlier. Okay, so it's a position that shifts, the equilibrium position, but the Ks still stays the same. The Ks only changes, like any equilibrium constant, if you change the temperature. Right, any questions, or any questions before we move on to another problem from the exams? So you clear between common ion and complex ion. Now, do you notice here, there was one 2013, here's one from the 2010 exam. The one in I think the 2011 was that zinc problem that is now in your teacher marked assignment. Okay, so this comes up exactly the same, and I'm not really going to go over it because can you see here's a common ion and there's the ammonia. So it's exactly as I explained in the first question. Okay, as I say, please make sure you write your equations down, and as I say, label them 1 and 2 depending on how many you write, and then just refer to that equation when you're referring to how the equilibrium position shifts. Okay, here's one now where they'll trick you. Okay, they first ask you, okay, you've got iron hydroxide will form when we've got iron nitrate dissolved in water, and they give you the pH. Now we haven't in this CH 3061 discussed pH yet. It comes in 3062, and then in your final one you get examples like this. But seeing we're also going to be doing this today, what does the pH tell us? Okay, water is neutral. Okay, so it tells you that it's a neutral solution. It actually also will tell us, as you do in the 3062, it'll actually tell you the concentration of OH minus. Now, this isn't really done at level 2, but if the pH is 7, then the concentration of hydroxide is 1 times 10 to the, 10 to the minus 7. Okay, and the concentration of the hydronium ions is exactly the same. It has to be identical because, as was said by Laura, it has to be neutral. So both of these. Now, what was the point? Right, so David, you're correct. What was the point of me trying to work out the concentration of the hydroxide? Because there's a reason why they told you the pH. So, okay, so you can find, well, the Ks value is given, okay, so we're given the Ks value, but it's because the hydroxide is for that insoluble salt, FeOH3. So we need to know the concentration of the hydroxide to substitute in, and I think that's what you might have meant, Leila. So remembering what we did last week, always write equation first, then expression, then the calculation. You'll just make fewer mistakes if you do that. So the equation we're thinking of, remember, is FeOH3, and it's an equilibrium with Fe3 plus and 3OH minus. That does sort of make it much clearer that you've got 3OH minus. You might have missed it if you hadn't written the equation. So, and I'm just going to write this down below because there's more space. So after the equation, what is the next step you write? So quite a few. Okay, yep, the Ks expression. So you would say Ks is equal to, and now it's the Fe3 plus and the OH minus concentration. Okay, and now you would just simply substitute. So we know what Ks is. There it is. So we've got that ticked. We can just substitute. We know what, I've forgotten something, in case I see the Layla's typing. I'll correct it now, and the rest of you can try and work out what is wrong actually. We've got the OH minus, that's over there. So has anybody worked out what I've done wrong? Okay, I haven't done the assumptions yet, but actually I have not put my 3 in there. Yes, okay. It's very easy to make careless mistakes. That's what I always tell my students. Always start a calculation from scratch again. You could have just done the wrong thing in the calculator. You might not have cleared it properly before you had started the calculation, or you might have pressed a wrong button by mistake and not realize that you've done it. So just always go back and check, because it's so easy to make mistakes. Right, so you just simply substitute into those, and then I think you can see it's simple enough to work out the Fe3 plus concentration. Layla, if it says you're typing when you're not, it probably is you leaving your cursor highlighter in the typing box. It may say now that I'm typing. It doesn't say it for me because I'm, but if you have that cursor box highlighted, it'll most probably say you're typing. So just click elsewhere out of the box, and then it should make it that you stop typing. Right, so you would just simply calculate that. Just regarding these sort of ions, you will not get in this new standard, because the 2012 was still the old standard. You shouldn't get any calculations relating to AB3 or A3B. So you don't have to do any where it's into quadratics and so on. So you've only got the most is a cube root, or raising to a power of 3 in total. Does that make sense? Because this would be, if you were doing a solubility, this would be, say, S times 3S cubed, which would have given me an answer of 9S to the 4. Okay, you won't get those sort of questions. Okay. Well, for the S, you might get something like this where you have to substitute, where you get given the value and then you just simply cube it. That should be possible. Right. What I want to do next, though, in terms of the complex ions, is question B. Discuss the effect of decreasing the pH of the water on the solubility of the iron hydroxide. So first of all, is a complex ion being formed? No. Okay. There are, of course, a lot more complex ions out there than the ZaK and the ZALP. Okay. But as far as you're concerned, you're only concerned with those, and you won't be given anything else. In this case, in this case, it's not a complex ion. It's actually just a recognizing if you decrease the pH, what's happening is you getting more and more hydronium ions. And what do you think hydronium ions will do to any hydroxide? Just remember, this is in equilibrium, so I have got hydroxide in solution. Okay, it'll react with the OH minus, and it'll remove the OH minus by forming water. And if I'm removing the OH minus, the equilibrium position is going to shift in such a way as to remove that stress, so by adding an OH minus, which means that my iron hydroxide will start dissolving. Okay, so David, you said we didn't find if a precipitate formed from A. Okay. Oh, thank you, actually. I didn't quite read the question because I was focusing on the I was focusing on complex ions. So I did not quite look at the question carefully enough. I said we had this and I was working out K, using the Ks. But if they ask you whether a precipitate forms, do I use Ks or do I use IP? I use IP. So what I had, so if I just do that expression again, so for this you just simply substitute IP instead of Ks, otherwise it's the same thing. So you'd have your Fe3 plus. Oh, please be very careful about charges when you're writing expressions. If your charges are wrong, the whole expression is marked wrong. So we've got this, and now I won't forget to raise to the power of 3. And if I just change my coloring, we've worked out my OH from there. Remember, that was 1 times 10 to the minus 7. We actually don't know IP because we've got to compare it with Ks at the end to see if it's bigger or smaller. So do I know, because we've got three things here, the IP, the Fe3 plus and the OH minus, do I know what my Fe3 plus is? So quite a few of you are typing. Okay, it's the one that's given over here, so I'll just change to another color. It's this over here. Now, again, knowing your solubility rules really helps. Okay, so if you see nitrate, you know that, and you know your solubility rules, you immediately think, all nitrates are soluble, which means if I'm given iron nitrate, it means I have exactly that amount of iron in solution. It's not that only some dissolves and some does not dissolve. So that's another thing you can learn. I'm making you learn all this rote learning, but your solubility rules just gives you that extra confidence. You don't actually have to know them off by heart, but it gives you the confidence to answer the question. So you'll know that that value gets substituted into the expression over there. Okay, I'm not going to be calculating that. You're welcome to calculate it, and it is, as I say, the 2012 exam. If you're trying to look for comparable, it's the 90700 standard. So if you just Google NZQA space 90700, you'll get all the past papers for aqueous systems, which is very similar. I don't think there's any real change to the present standard, the one you're doing now, which is a 91392 standard. They're pretty much identical. Right, so any questions on that before I move on to acids and bases? So you've worked out a precipitate will form? Good, Laura. I haven't actually calculated it. Okay, so for this 3061, you have to be able to work out solubility, in where it only comes from one source. So that's a dead easy one. There you can use the simple where you'd say Ks is equal to S squared, or the Ks is equal to 4S cubed, depending on if it's an AB or A2B salt. Then you'd have to also work out when the ions come from two separate sources. And I know I've marked a few 306 and remember when you're mixing two solutions, if I have equal amounts of solutions, when I mix them, my volume is doubled. which means my concentration is halved. Students haven't been really noticing that, so just make sure that's sort of the only trick they really ask you. Or they might say 20 mils is mixed with 40 mils of another one, so those are slightly, you've got to apply more of a ratio there. Otherwise, I'll ask calculations in terms of complex ions, in terms of, common ions, or it'll be discussion in terms of complex ions or common ions. And that, as I say, is normally a question all by itself out of the three. Okay, so while Layla is typing, I'm going to just quickly swap over to another document. Okay, a few of you are typing still. Right, well, okay, sorry Layla, so it's not working when you go out of the, try and click out of it. Okay, right, so this is now the 3062, and before we go on to that, what is expected to know, and I start off the booklet going over level 2 stuff, so if you can't remember everything, this is all introduced again. But what is expected for level 3 is that you know a definition of an acid and a definition of a base. So what is an acid? If any of you can remember from level 2, which may be a long time ago, it's a proton donor. Okay. Another way to put it, because there are different definitions, Arrhenius says if an acid is put into water, hydronium ions are formed. Okay, and if a base is put into water, so thinking of the Arrhenius base definition, what is formed? Hydroxide, correct. And then you've got the Lowry-Bronsted one, which is what Laura said, if an acid is a proton donor, and a base by the Lowry-Bronsted definition is a proton acceptor. Okay, so as far as you're concerned, because you're working mainly with, aqueous systems, the Arrhenius one of forming hydronium ions or hydroxide ions works pretty well. If you're carrying with university, you'll do other definitions, and it's a much broader definition. But these are perfectly adequate. So that's a definition of an acid and base. What about the definition of strong or weak? So if I said I've got a strong acid or a strong base or a weak acid or a weak base, so what is strong? Okay, it completely dissolves is not quite correct, Laura, because you could get something that dissolves completely, like ethanol. Ethanol completely dissolves in water, but it's not considered to be strong. So it dissociates completely, or it ionizes completely. So, for instance, HCl not only dissolves completely, but the H and the Cl separate completely, so you've got only the H+, which attaches itself to water, because H+ is only a proton, so it forms a hydronium ion, and you've got chloride ions. There is never any HCl as a molecule in water. So it only exists as H+, H3O+, or Cl-. Don't worry, Laura, I actually like it when people make mistakes on here or ask questions, because it does clear the concepts up. So please always be willing to have a go, so I'm glad you did it. So that's strong. It dissociates completely. So strong base would be something like sodium hydroxide. It will fully dissociate to form sodium ions and hydroxide ions. What is the definition of weak? It only partially dissociates. So if I had something, for instance, like ammonia, ammonia is a weak base, so it means in my solution, although it's fully dissolved, I've got ammonia molecules, and I've got NH4 plus ions, and I've got hydroxide ions. Or if I had a weak acid like vinegar, I would have, or ethanoic acid. Okay, that's correct, David. The equilibrium lies very much to the left. So if I had ethanoic acid, I'll have the whole ethanoic acid molecule present in the water, as well as some ethanoate ions, as well as some hydronium ions. Okay, as I say, most of the weak bases exist mainly as the molecule or the undissociated substance, and only a little bit dissociates. Well, certainly the ones we work with, because the ones that are sort of a bit in between get a lot harder to calculate because you're not allowed to make assumptions then. Now this table over here is given from pretty much the exam people, in that when they write the exam, set the exam, they expect you to know those. So you've got to learn complex ions off by heart, and you've got to make sure you know these. So if I said strong acid, you should be able to list off HCl, HBr, nitric acid, and sulfuric acid. I gave a few more in the booklet because I wasn't quite sure if they'd ever changed, so I gave, like, for instance, perchloric acid. But it's at the moment, if they gave you perchloric acid, they would state that in the exam as it being strong. Similarly, if I said KOH or NaOH, it's expected you know they're strong bases. And then, as I say, these bases, they expect you to know are weak. So if I said ethanoate, you'd immediately think that's a weak base. Or remembering also your organic chemistry, okay, aminomethane or methanamine, both names are acceptable, is a weak base, and ammonia is a weak base. And then those are the weak acids that you have to learn. Who knows all of those already? Because you came across them last year, but as I say, last year is a long time ago. Okay, you know most of them. Good. Okay, so as I say, if you're not sure, make flashcards and learn them. So you've already got lots of flashcards that you've. So I hope your rooms have got lots of flashcards or lots of charts on them with all these things you have to remember. It's not quite as bad as biology. Do you actually have to learn formulae in physics for anybody doing physics? Do you have to learn all those formulae off by heart? Or are they given to you? Oh, okay. They're being nice in physics. Okay. Then the other thing is, after you've learned your acids and bases and which ones are strong and which ones are weak, is you've got to know what is a conjugate acid and a conjugate base. So, sorry, I clicked in the wrong place there. So, a conjugate acid, or an acid and its conjugate base are always a pair. So, would ammonia and H2O be conjugate? No, because H2O has got nothing to do with NH3. There's no similarity there whatsoever. What would be the conjugate of ammonia? And of course that line there now is so I know, right, NH4, because can you see NH3 is pretty similar to NH4. There's only a difference of an extra H+. So look at the two substances you are saying are conjugate and check that there is a similarity in terms of atoms in there. If they are not, then you've picked the wrong pair. So if ammonia is a base, which you've hopefully will learn, okay, from there, then it has a conjugate acid, which means if the ammonia reacts as a base by accepting a proton, then it forms NH4 plus. And can you see the difference between NH3 and NH4 plus? Is it added H plus, and H plus is just simply a proton. So if it's accepted a proton, it's formed NH4 plus, can you see that NH4 plus can lose that proton to form NH3 again? Okay, David, that's a good question. Which one is stronger? You'd actually have to know the Ka and the Kb values, which I'll go on to. A strong acid will always have a weak conjugate base. So pretty much if I drew a chart like this and I made, say, acids over here and their conjugate bases over here, and I did it in terms of strength, so the further out you go, the more concentrated it, the stronger it is, not more concentrated. So the higher you go, the stronger it is. So a strong acid would have a very weak conjugate base, okay? And a strong base, so we're over here, would have I'm trying to make it a very, perhaps I should, just to make it an easier thing, so if I made this strong and weak over here, and then I perhaps made it strong over there. Actually, that should work. Strong acid has a weak conjugate base, a strong, I don't want it to come on top of each other. So strong base will have a weak, okay, if I made it strong and weak, would that fit? The strong acid has a weak conjugate base. So it would, say, be over there, because something strong would be something weak, whereas a strong base would have a weak conjugate acid. So if I've swapped them around, and it follows pretty much a line like that. So if something's a weak acid, its conjugate base is sort of also in the weak line. It's sort of in between. So does that make sense? So it depends exactly where it's at. It's of how weak it is. So as it goes up in strength, it goes along in weakness as a base. Does that make sense? Yep. Okay. So HCl, for instance, is a strong acid. So chloride is an incredibly weak base. It hardly acts as a base. Okay, it won't actually accept a proton because by definition HCl has to dissociate completely. So the moment I try and make chloride act as a base to accept a proton to make HCl, and sorry, that's supposed to be an HCl. Oh, come on. HCl plus OH minus. What is a HCl going to do with the OH minus? So if I try and have chloride, I try and react it with water to make the HCl and OH minus. Is that going to work? Yeah, so donate a proton. Yes, the HCl would donate a proton to the hydroxide. You know that HCl and hydroxide react straight away, and it's going to go straight to chloride again. Correct. So both Layla and David correct. So Cl is such a weak base, it doesn't even really deserve the term label base. So a very strong acid has a useless base, and a very strong base has a useless conjugate acid. Okay, right. So that is going over the level 2, and the final thing we know from level 2, or the final two things, but they are related, is the pH scale. I think all of you know the pH scale. What values are associated with an acid? It's less than 7, correct? What values are associated with a base? More than 7. And then neutral is 7. Okay, and you did last year some pH calculations where you used that formula. And as I say, using logs and anti-logs are perhaps the most difficult chemistry or most difficult mathematics you have to do. Unless, of course, you didn't know how to do cube roots or cube something. So that's about the highest level of mathematics you have to do. Okay, So that's level 1. Level 2, sorry. Let's move it on to level 3 now. So just like we had the solubility equations and the solubility expressions, we have exactly the same thing with acids and bases. Because there's an equilibrium, we can write an equilibrium, an equation and an equilibrium expression. So looking over here, first of all, Kas, they are only for weak acids. Why don't we have them for strong acids? So if I had HCl, why can't I write, sorry, that's not very good writing. Why can't I write an expression for my HCl? Okay, Laura said there's no HCl. Okay, correct. In that there's really no equilibrium. The equilibrium is just so far to the right. It's so enormous that actually in water, it's limited by the water because it's just so far to the right. So we only use it for weak acids. HCl is something like 10 to the positive 8, 10 to the power of 8. It's something enormous, and it's a pointless concept to have an HA for strong acids. So we only use it for weak acids because there at least the ions would be in equilibrium with the molecule. So if I, for instance, had, let's make it any weak acid, HB will be in equilibrium. I'm going to still have HB present, and I'll have B minus present, and I'll have H3O plus present. Okay, right, and according to that equation, can you see then that we have, we use this Ka expression to find out concentrations of HB, or the hydronium ion, if you're asked to calculate a pH, that's when you use this, and also perhaps the B minus, you might be asked that. So this is why we use a Ka expression. And it's done exactly the same as with the Ks, except with the Ks we had a solid as a reactant and was underneath, and we don't have that with the Ka. We do have water. So does water change in concentration? No, it's so minimal we can assume it hasn't changed. If we made something extremely concentrated, say for instance totally concentrated sulfuric acid, that's something like 18 molar or moles per liter, yes, you could talk about the concentration changing, but actually even there it'll be minimal. Water has got round about 55 moles per liter of water molecules in a liter. So that's an enormous amount, so it's pretty constant. Okay, so what we can do is we can take that out, put it into our equilibrium constant, just like we had with the Ks, and this now forms a new constant called the Ka, or the acid constant. Okay, and if I just go down a bit, I hope that's clear enough. I'll make it a little bit bigger. Okay, one thing you have to note, because we're going to be going on to the Kb just now, Ka always has H3O plus at the top. If you don't have H3O plus at the top in your expression, you have not got a Ka, and you can't substitute a Ka into it. So always check that your expression, once you've written your equation, that it finishes up with that H3O plus at the top. If it doesn't, you haven't got the Ka. So it's always the hydronium ion at the top with the conjugate base, and then the undissociated acid at the bottom. Any questions for that on how you would work that out? Do you think you could work that out for? Okay. Right. Just as a pointer for the exams, I don't really like always teaching for the exam, but I think those are sort of tips you'd need to do well in the exams. You will never get something where you have square root squares or so be something like that. You would only have the 1-to-1 ratio. So that makes it hopefully a lot simpler for you. Right, let's go to the, yes, it's at least nice and easy. If you go to the KB now, it's identical, except of course we're using for a base expression. So again, we're using now for weak bases only, okay, and using those same things of B standing for a base that's combined with an H to form an H thing. We can use it to work out now the hydroxide concentration. So remember that iron hydroxide one we had with solubility. I doubt that they would ever merge the two together and make you put iron hydroxide into a weak base solution. That's highly unlikely, but I'm using that as an example. If you needed to calculate the OH minus concentration, you'd use the KB expression when you are given a weak base. So again, remember, you always write out the equation first. So if we were doing it in terms of the general one, it would be B minus plus H2O. At level 2, you could get away with not writing the H2O, and it's not ultra important at level 3, but you do have to try and make sure it's balanced. So at least by writing the H2O in, it becomes balanced, plus OH minus. Okay, check your equations. Are my charges balanced? In other words, is the charge on the left-hand side, if I add up all the charges on the left-hand side, does it equal the total of the charges on the right-hand side? Yes. So it's a good tip to remember is always, because if you were asked to write this out, this would be an achieve level sort of thing. But if you just forgot, because you were in a rush, you forgot to write the B minus or the minus charge or the minus thing over there, it would be marked wrong. So just always double check. I've got one negative here, that's neutral, the H2O, so it's a total of one negative on the left-hand side. On the right-hand side, HB is neutral. I've got one negative on the right-hand side, so I've got a total of one negative on the right-hand side. Okay, so you'd start off by always writing the equation, and then the same sort of thing as what we did before. We've got water there, that's a constant, so we can put it into the K as a constant, and that constant of K H2O becomes the KB value. Now, remember I said Ka always has a H3O plus on the numerator. What would we always have for a KB? The OH minus. If you don't have the OH minus, then you've made a mistake somewhere, or you're not calculating the KB, you're calculating something else. So KB always has the OH minus. And that's important to know, because in the exam, they will never give you a KB. They'll give you bases, but you are expected to derive the KB. There's two ways you can work out with bases. You can derive the KB from the Ka, which we might do today or might do next time, or there's a totally different approach that I haven't taught, and a lot of students forget that. So they'll just simply plonk in the given Ka value that's given, but because of the equation they've got OH minus, and can you see that's not going to work? I can't substitute a Ka value for a Kb when I've got OH minus. Okay. Are you all okay with deriving that equation? Or remembering that equation? Just by simply being able to derive it makes it just a lot less to remember. But after you've done a number of problems, you'd know it off by heart. Okay, very quickly in the last 3 minutes. this is the relationship between the Ka and the Kb. Okay, pretty much the Ka times the Kb is the Kw. So I can say Ka times Kb is equal to Kw. Now Kw is a thing we haven't done yet. What do you think Kw would stand for? The water, the equilibrium constant for water. Water exists pretty much all as H2O molecules, but there is a very tiny bit, yep, 0.1, sorry, 0.000000000, count 14 noughts, one of a water molecule will break up to form the OH minus and the hydronium and the H plus. So it's a tiny minuscule amount, but so that Kw comes from water and breaking up to form the H plus, which immediately joins onto another water molecule to form the hydronium ion, and OH minus. Okay, so that equilibrium constant, if you can imagine, we can do the same thing. K is equal to the H plus times OH minus all over H2O, but remember H2O is a constant, so we can simply cross that out. Oops, I tried to change into a different color. We can cross that out and make that Kw. Okay, and that is, as David said, 1 times 10 to the minus 14. And what I've tried to show here, this explains how we can get the Ka, so I hope this makes sense. If we worked out the Ka and we worked out the Kb, you should then be able to get everything cancelling except for the hydronium and the hydroxide, and that gives us our Kw. So if we want to get the Ka, we simply take the Kw and divide by the Kb. More likely, because you're always given the Ka, if you're wanting to get the Kb, you would take the Kw, which you expected to know, 1 times 10 to the minus 14, and divide it by the Ka, which will be given. Okay, we'll stop there because it's 3 o'clock. Any questions? No. Okay, so next week we'll go on to some calculations. Okay, so we'll look at Ka calculations, Kb calculations, and then also a very important part that's guaranteed to come up is species in solution. Okay, all have a good week, and remember exams are in about 3 weeks' time, so I hope you're getting those flashcards going. Okay.